Hi, I am Hafiz. This is the part 2 of Logical Gates video series. In part 1, I have given a brief introduction about what is logical gates, and also we discussed discussed the gates in the basic gates category and not operators. Today, in this video, we are going to talk about the universal gates, and also there's another special type gates that we will be discussing in this video. The first gate that we are going to discuss is the NAND gate. This is the combination of not and operators. This is the symbol of NAND gate. So in this gate, in AND gate, what we do is we multiply the input data. So in NAND gate, we get the opposite or the inversion of that multiplication. So that's how the NAND gate process the data. This is how the symbol has got created. So the usual AND operator is something like this, the semi-oval shape. And if you have gone through my part 1 video, you will see the NOT operator is something like this. So the NAND operator is the combination of these two, and finally you get this new symbol. Now let's see the truth table of the NAND gate. If you pass A0 as the A data and 1 as B, you will get the multiplication 0 into 1, it's 0. But since here we are getting the opposite of the AND, you will get the value 1. So likewise, if you pass 1 and 0, the multiplication is 1 into 0, 0. But the opposite, it's 1. 0 into 0, it's 0. The opposite is 1. 1 into 1 is 1. And the opposite is 0. So in the coding, we represent the NAND gate as like this, A dot P and the bar. In universal type gate, the next one that we are going to talk is no operator. This is the combination of NOT and OR. In as I mentioned in previous gate, the NOT operator looks like this, the symbol, and the operator looks like this. You might remember that I mentioned that it looks like a spaceship. So the no operator is a combination of these two, and you will get this new symbol here. This is nothing but the opposite of the O operator. In O, you will get the addition of the input data as the output. But here we are getting the NOT part, which is the inversion. You will get the opposite of the output of OR gate. We represent the coding as like this, A plus B and the bar. Let's see how the truth table looks like. If you pass 0 as A and 1 as B, so 0 plus 1 is the typical OR gate. Here it should be no gate. So 0 plus 1 is 1, but here we are getting the inversion, you will get 0. And if you pass 1 and 0, 1 plus 0 is 1, and you will get the inversion 0. And if you pass 0 and 0, it should be 0. But since you are getting the opposite, you will get 1. 1 plus 1 is 2. In usual operator, we consider 2 as 1 since we are dealing with binaries. But here we are getting the opposite or the inversion. So the 1 becomes 0. So that is how the NOR gate works. Next, we are going to talk about the special type logical gates. This EXO or SAW, we call it as exclusive OR. It's an extended version of OR operator. If you take the symbol also, the usual OR symbol is like this, but additionally you have this additional curve line in here. And when encoding, when we represent this operator, for the usual operator, we have this A plus B, but for the plus mark, we put a circle. The rule in here is, in a usual operator, we add the input data to get the output, but in exclusive OR, if the input data is equal, then the output data will always become 0. So that's the additional rule in here. If the input data is 0, for example, if the A and B are equal, then the output will be always 0. So that's the exclusive operator, logic of the exclusive operator. Let's see how the truth table looks like. So as per typical OR gate, if you pass 0 to A and 1 to B, 0 plus 1 is 1. So that will be there. It's no problem. And if you pass 1 and 0, the 1 plus 0 is 1. It will be there. And then if you pass 0 and 0, so 0 plus 0 anyway is 0. But based on this, the rule of XOR gate, if the input data is 0, then it is 0. And if you pass 1 and 1, since the input data is equal, so you will get the 0 as the output. In the typical operator, if you pass 1 and 1, you should get 1 plus 1, 2, and we consider it as 1. But since here the rule in here is, if the data is equal, then your output should be always 0. So if you pass 1 and 1, it's 0. This is the final gate that we are going to discuss in this video. This is another special type logical gates called XNOR. This is nothing but the opposite of the gate that we discussed previously, the opposite of SAW operator. This we call as exclusive NOR. This is, if you take the symbol, so for the typical SAW operator, you will have this additional circle in the symbol. Coding level symbol is like this. So A, so B, the bar. So how this will work is, it will get the opposite of XOR gate. Let's see how the truth table looks like. If you pass 0 as the A value and 1 as B value, so based on the rule of exclusive OR, you should get 0 plus 1, it's 1. But since here we are getting the inversion, it will convert it into 0. And same as if you pass 1 and 0, it should be 1. But since you are getting the exclusive, the inversion, the value will become 0. And in XOR operator, if you pass same data as input, then you will get a 0 as the output. So for the last two lines, you should get 0 in as per the XOR operator. But here, since we are getting the opposite ones, it will converted into 1. This is how the XNOR logic behind the XNOR works. And that's all in my today's video. So this is the part 2 of the logical gates. I suggest you to first go through the part 1, then you can get a better understanding of the basic logic gates and the some detail what it does and how it works. So this is something like a combinational gates of the basic gates that we discussed in the part 1 video. Meet in my next video. Thank you very much.